Now we have our last talk of the first part of this afternoon by Roberto Velho from KAUST also, and he's going to talk about mean-field games.
Again. So we're not intending to create a mean-field game session, but I think that's what we made. Because also there is a talk of Edgar later on. Okay. So I start this work actually in Lisbon with Diogo Gomes, my advisor. And some of the results we show were done with Marie-Thérèse Wolfram from Rican in Austria. I decided to do a really pedestrian way of where are mean-field games and try to motivate and show where they come from. And also present some discrete case that I don't see in general people presenting that. And that's mainly what I'm doing now. So what's the idea of mean-field games? So today this is this class of system that of PDEs to understand the collective behavior where each agent has the same cost function and try to optimize for himself, but agents don't cooperate. So when you try to act, you depend on the choice of other agents. I mean, you are in a physical space. For instance, people are in front of you. You can just not move. You depend on other people. So seminar work was Larry in Lyons, that is mathematician group, Paris, and Huang, Mallamé, and Keynes, that is actually an engineering group in Canada. They came in at the same time, completely separate. Okay. So I think actually David presents some things, but what are mean-field games? They are mainly these monsters. And so we have a so-called first-order mean-field games and second-order mean-field games. That's mainly a Hamilton-Jacob equation coupled with Fokker-Planck, or just advection. And my idea was try to motivate them and show where they come from. They're just not big monsters. Okay, so for this I will try in 4 slides to show a bit of calculus variation and optimal control. So if you have a simple function in R to R, we know that if a point is extremal, you need just to calculate that, and you have a necessary condition. If you have a function Rn to R, you know you have to study the gradient of the function. But now if you have a functional, so we can do the similar thing. You take a Taylor expansion, you analyze what's the first order of the Taylor expansion, and we end up in the so-called Euler-Lagrange equation. So the Euler-Lagrange equation is similar to these conditions in R to R or in Rn to R, and just tell us what's the condition for a minimum or maximum. But now we have a function, not a point anymore in Rn. Okay, and it's OD you have to solve. Okay, I'm telling now one agent because as David told, so this is, you're performing like one optimization, find one function. So as one person is trying to optimize something. But now imagine you have to walk in some domain, and you have a cost of walking and the cost the place you reach. Okay, so you have an expression like this for the total cost. Okay, and if you want to calculate where the trajectory is to minimize these, you can just use the Euler-Lagrange equation before with a boundary condition and discover what is that. But there is another way also. So imagine we set this function. So this is a bit, I'm showing the heuristic of that. Okay, you set a function that we call the optimal cost at a certain point, and we intend to choose a velocity such that you can minimize this cost of walking. Okay, over the paths that initial condition fixed, and the endpoint is arbitrary, and there is a boundary condition. So if you are in a point t0, x0, and you walk by a velocity v, we have a cost of that. So from t0, x0 to t0 plus dt, x0 plus v dt, you have a cost, okay? You can perform the same ideas before with Euler-Lagrange. So you take a Taylor expansion, and you forget about the high order terms, and then you see that you end up in this expression here, okay? And the idea is to choose G is V to minimize the expression, okay? So as you see here, you can create this function called the Legendre transform, and you can calculate what's the minimum to minimize this function, okay? And you plug there again, and you discover that you eliminate these terms, and you discover that the condition, as in the Euler-Lagrange, to have a minimum maximum is this one, okay? But now we have a Hamilton-Jacob, that's so-called Hamilton-Jacob equation. So we don't have the Euler-Lagrange. The Euler-Lagrange was an ODE. You can connect to the Legendre transform to a PDE. There are benefits of using one, benefits of using the other one. And you can also calculate what's the optimal velocity to walk, okay? This depends on regularity issues that I will not discuss here. But it doesn't change the equation. So either you're able or not to do it. Okay. You could also do a Stochastic perturbation. So instead of walking VDT, you can also perturb with a Brownian motion. And instead of calculating the cost, you calculate the expectation of the cost, because you don't have an idea of the cost as a deterministic function anymore. Okay. So you use a Taylor expansion and the Ito lemma to treat the chain rule for the Brownian motion, and you end up in the so-called Hamilton-Jacob-Bellman equation. So the only difference is this term. So you add these, so you gain these to the equation. And a good surprise is that yeah, sorry, it's missing Laplacians too. Thank you, forgot. The good surprise is that the optimal velocity is still the same. It doesn't change. This comes from the character from the Brownian motion. So since you are doing a perturbation that is similar probability other directions, so the optimal velocity doesn't change. Okay. Okay. So we learned how it works for optimizing or choosing an optimal trajectory. Okay. But now imagine you have, as Davi was trying to explain, several agents playing. Okay. So if you have several agents playing, imagine they have the same cost, and if you're in a given point, then they need to have the same velocity. Okay. So I'll do a distributional approach here. So imagine you have a mass of agents, density, and you can approximate by this function. Okay. So if you differentiate with time and use the fact we know the velocity, you plug here, and so this is just a heuristic way. You take the limit n goes to infinite, and you realize we end up in the distributional way with this equation here. That's the advection equation. If you perform the same thing in the stochastic case, you end up with the Fokker-Planck equation. Okay. So, so imagine you are in this auditorium and it's a really boring talk, and you want to escape from here. Okay. And you probably want to set a velocity that's not that high because everyone is going to see you. But if it's really boring talk, someone also is trying to escape, and this person will be on your way. So that's the idea of the mean field games. You want to perform optimization, but you have to take in consideration other people. Okay? So the main difference for what it presents is that now you have to consider is a mass of people that can interfere with you. Okay? So that's the way you come back to that system. So we have the Hamilton-Jacobi that show you how we got, and Hamilton-Jacobi and the Fokker-Planck equation. Okay. So why to study these systems? So they deal with equations that are interesting per se. So people studying Fokker-Planck equation, Hamilton-Jacobi, there is a lot of problems to solve. They also brought some new ideas of calculus variation. So there are mean field games that you can reduce for the classical calculus of variation form. And there are some problems in calculus variation that can be regarded as a mean field game. And you have an interesting way of seeing that. I mean, this is if you are like a pure mathematician, but there are people using application of that. So like Carmona, Fouque, and Sun, so about systemic risk in finance, or crowd motion, just to say some of the works. Okay. I also like to show the discrete case. So Lyons created that idea in 2006, and my advisor about 2008 decided to try to understand that. Things are really difficult, and decide, okay, let's do the discrete version of that. And I decided to present just a two-state problem. So we have only two states, and you have to decide if you jump to the other one. Okay. So one regard, so you have when you have the optimal velocity, it shows here, and you have a term that is the Hamiltonian, the Lagrange transform. So we have the same thing here. You have the optimal velocity, that's again the derivative of the Hamiltonian, and you have a term of the Hamiltonian that is just the Legendre transform of the cost. What is missing today on this is that we don't have a good notion of solution to this equation. So it's a parabolic system, and no one knows what's a good notion of solution. Okay. In the case of only two states, you can try to do a reduction, like just writing the difference of 2U1 and U2, and you adapt in conservation law. You can write a Hancock-Hugoniot condition, but we don't know much about that. Okay. So these are just the work we're done. I revised in 2010, write the discrete time, and later on the continuous time. And he showed that, so something I didn't talk, there is the Nash equilibrium. So for the n system, instead of the limit, there is a notion of equilibrium as in gas kinetics, that is the temperature. So there is a notion of equilibrium, that's the Nash equilibrium. And my works for Diogo and Marie-Thérèse were to create a numerical method for this discrete system. So people in the continuous case were in general studying the ODE, or the characteristic associated to the continuous case. We create a method for these discrete system. And the idea was use the n-place structure for the hyperbolic system, okay? Instead of just discretizing the PD, the limit PD. But you need a way of comparing these discretization, and there were no methods. So we got a so-called potential mean field game that can be reduced to Hamilton-Jacobi, and then you can use the classical discretization from Hamilton-Jacobi to compare. And you have a quite good result. So the resolution is the resolution of the discretization. Okay. You also wrote some work about dual mean field games that try to give some light on how this PD works. So just some application. I think David talked. I had application in economics, and the idea was just like, imagine you have two phone companies, you have to decide if you jump to one to the other. That's like a two-state. So the idea, if you have a cost function, people in economy study, you end up knowing something like this. If you have, you might have a critical value to jump or not. So if certain amount of people, if there is a proportion of people less than certain number, it's not worth to jump. So you can use for problems in economy. Another thing I'd say, that's what I'm working. So there's this structure behind the equations, but you need some infinite-dimensional version of what Ambrosi and Figali are talking about, depending on Lyon's theory. And I'm working in discrete case, what's the limit, and also in crowd motion. So there are some attempts to use mean field games for crowd motion, but I think no one could prove this system, that's the so-called Higgs mod, is a mean field game. But I'm working on it, but you need, you have some issue on that because you have an equal, and you have to treat these with measures. So, but Figali has a work on how to treat these Euler-Lagrange with measures. Yeah, that's it. Thank you.